Okay, I'm Doug Richards. If anybody wants to email me, my email address is there, doug.richards@cox.net. I'm going to be talking about Weak Signal Propagation Reporter, known as WSPR, and its implications for anomalies research. Now, this is something that most people who do it just think of as a way to measure radio propagation, and I'll explain a little about what that is, and then I will talk a little bit about how this might be useful for some anomalies research, because it turns out there's a lot of overlap in things that you might want to measure with it. And it also offers some lessons as to how anomalies could be approached. What you're seeing on the screen right here is some examples of maps generated by WSPR. The one on the left is a station at an Antarctic research station, and it's all the signals that are stations actually that are receiving him at a particular moment in time. The one on the right is an example from a couple days ago of all the stations receiving me during a 1 hour period. So on we go. So what is the Weak Signal Propagation Reporter? Well, it's a signal processing algorithm for extremely weak radio signals. And there are hundreds of stations worldwide uploading to this WSPR-net database, and anyone can download. And so I'll explain later that you don't have to be a ham radio operator to use the database. You do have to be a ham radio operator to transmit, but you can either use a receiver or just the internet in order to receive the database. And so this slide here is an example of one of the things that you can download, which is a map for any particular time period of people that have heard anyone from anywhere. And in this particular one, you can't see me in there, but I'm in Virginia Beach. And these are people that heard me in a 1 hour interval a couple days ago. So it ranges from all the way down in Australia to Brazil, to South Africa, to Germany, to the Canary Islands, Costa Rica, Alaska, and all over the United States. And so you can use this to measure how well radio signals are propagating to any of these locations. And that's its designed purpose, so that radio operators could see, for example, yes, I have a good path to Hawaii right now, or a good path to Australia, if I wanted to talk to someone there. Now, that's what it's for radio. Question is, why is it relevant to anomalies research? Well, much anomalies research also tries to detect very weak signals. The whole basis of research into psi is figuring out statistical ways of taking an incredibly weak effect and bringing it up to the point where we can identify that there's actually something there. Some of the global consciousness work, I saw Roger Nelson give a presentation last week, and they too have these random number generators all over the world. And the idea is to use a statistical method to bring out of this very, very noisy data a signal that shows that random number generators are reacting to various events in the world. Another thing that happens is there's been research looking at effects of the geomagnetic field on things like psi, heart rate variability, all sorts of other physiological variables that were thought to really not have anything at all to do with the Earth's geomagnetic field. And so, again, you have very weak signals there and connections to geomagnetic variables, which is what radio has too. So there's really quite a bit of overlap in terms of what they're trying to accomplish with WSPR with radio signals that are affected by geomagnetic fields, and what's being accomplished with a lot of anomalies research. Now, there's a couple things you could do with WSPR. One is you can actually apply it directly to studies of the effects of the geomagnetic field and ionospheric resonances on biological systems. And I'll talk a little about what that would be later. For example, looking at psi, looking at heart rate variability in relation to, say, a solar storm and what that does to our ionosphere. And also, it can provide useful methodological comparisons to other studies of very weak signals. For example, detection of synchronization of global consciousness detected by random number generators all over the world. Some of the methods used for that could be applied to having WSPR receivers all over the world trying to pick up signals. So there ends up being some potential overlap here. Not saying that something like psi or global consciousness is based on radio signals, but you've got a number of the same issues, and it looks like some of the same variables, such as the geomagnetic effects, may be relevant to both radio and some of these more anomalous kinds of phenomena. So, a little bit about radio signals. In the earlier conversations that we were having in the lounge, There were some people there who have some experience with this and actually also have ham radio licenses like I do, but some of you have probably never heard of this before. And so the idea is that for some radio signals, for example, your cell phone, it has to be within line of sight of a cell phone tower. And if you're out of line of sight of the cell phone tower, there's no radio signal. But for other frequencies, the frequencies go from the transmitter up to the ionosphere, a couple hundred miles up in the atmosphere, where there are ions, and the ions bounce radio signals back to the Earth, then they bounce back up to the ionosphere, and then back to the Earth. And sometimes they can make multiple hops and go actually not only halfway around the world, but all the way around the world. So you can sometimes hear an echo of your own signal a few seconds later from having traveled around the world. Now, this varies an enormous amount in terms of what signals can go where at what times. And so the whole purpose of WSPR was to be able to measure this with a big worldwide network, so you'd be able to figure out, this would be a good time, say I want to talk to Hawaii or Antarctica, that I would be using my radio on a particular frequency, and you'd use WSPR to measure whether this was a possible thing to do. Now, one of the major things that affects the ionosphere and affects the ability of all this to work is solar radiation. And solar radiation, I'm not going to get into any of the details of how the sun works today. That gets into a whole complicated area. But the idea is that it affects the ionosphere and can produce geomagnetic storms, and that changes radio propagation. Now, that's been known for a long time, but more recently, it's been discovered that if you look at the measures of geomagnetic storms, you also see correlations with psi functioning, for example, the dream telepathy experiments of Stan Krippner, and various aspects of human physiology like heart rate variability. So it looks like some of the same factors are affecting not only radio signals, but are affecting some of the more anomalous phenomena that we want to look at. And so a system that can measure what's going on might be quite useful for anomalies research as well as for radio research. So, how does WSPR work? Well, the challenge is you've got some very low and uncontrollable signal-to-noise ratios in long-distance radio communication. Now, that's in contrast to lab experiments where the signal-to-noise ratios are higher, they can be controlled, but it's very similar to issues in psi experiments. So what a physicist will do is do a lot of work to eliminate all sources of noise. The trouble with the real world is that you can't do that. And so radio is a great example where you're basically stuck with whatever kind of noise is out there, and you have to somehow deal with that noise. And the solution for radio was developed by a physicist named Joe Taylor at Princeton University. He won the Nobel Prize and is a radio astronomer and a physicist. And what he uses is something called forward error correction and other signal processing techniques to make possible decoding of signals about negative 31 decibels below the noise level. Now, for those who aren't engineers, that may sound meaningless, but it's basically what allows you to have error-free internet communication and a lot of other sorts, cell phone communication. The difference is that your internet and cell phone communication still have to have a pretty low noise level to work. Whereas what Taylor did is he came up with a system which, by using fairly long blocks of signals and a number of other signal processing techniques, made it possible to actually decode signals that are so far below the noise that if you listen to them on the radio, all you hear is noise. There's just absolutely nothing there as far as you can tell. But by these various types of signal processing, it's able to actually pull the signal up out of the noise. So what he then did is he released his software for free, and you can download it on your computer. And this uses the regular ham radio bands, a very, very tiny section of each ham radio band. And ham stations around the world transmit and receive signals. And when they spot signals of received signals, they then upload them on the internet to what's called WSPRnet, which is a website. And then WSPRnet data can be downloaded and analyzed by anyone. So this is not just something that ham radio operators can use, but it's something that anyone can use. And there's actually a group now based out of the University of Scranton where one fellow did his dissertation looking at thousands of data points and seeing how WSPR responded to various kinds of solar storms. So anyone can download the data. So What's this for? Well, as I said, the intended application of WSPR is to explore effects of these various phenomena on radio propagation. So, for example, one of the major things that affects radio propagation is geomagnetic field variability. And classically, the idea is that when you have a geomagnetic storm, radio propagation gets very badly messed up. Well, it turns out, and I've been running WSPR 24 hours a day for about a year to get a good baseline. That's not necessarily true. Sometimes you actually get enhanced propagation in a geomagnetic storm in the middle of the night when there's nobody on except for the people who keep their WSPR transmitters running. And so you'll find that at 3 in the morning, all of a sudden, there is a geomagnetic blip and suddenly some very good reception all the way down in Antarctica. And so some of these are very unpredictable because people are running these stations all the time. You detect things that people wouldn't have detected otherwise. Time of day is another variable. For example, the band that I've been using, what's called the 20-meter band, is generally very good for long distance during the day and useless at night. I'm finding actually that at times it works very well at night, but it's kind of sporadic, and we're not quite sure why. Sunspots have a huge effect on it. We are now ending a sunspot minimum where there were basically no sunspots and slowly climbing into the range of high sunspots, an 11-year cycle. So in about 2025, they're expecting there to be a high in the sunspot cycle, and that generally causes extremely good radio propagation. Now, we don't know what effect that has on psychic functioning, for example, but there's certainly some good data on a number of other physiological variables that suggest sunspots can affect them too. Time of year has a major effect. Sidereal time, that is star time, may have an effect on radio propagation. And it looks like it also has an effect on psi based on some studies that have been done. So these same variables that WSPR is measuring may affect human behavior and rhythms, including psi and health. The big advantage of WSPR is that WSPR is able to make fine-grained measurements much finer than what are called the K-index and A-index. And again, most of you probably don't know what those are, but these are ways of measuring geomagnetic storms, and they are done in 3-hour intervals. And so the finest grain you can get is within 3 hours. WSPR is typically running a signal every 10 minutes. You can actually set it to run a signal every 2 minutes, although that tends to clog up the band a little bit. So most people only run it every 10 minutes to allow more space for more stations. But you can actually get measurements as fine-grained as every 2 minutes instead of every 3 hours. So, for example, if you were running a psi experiment, you could actually look every 2 minutes and perhaps pick up some effects that you wouldn't otherwise be able to see. Whereas in the past, people have used what are known as the K or A index. There's another one called the AA index, and they're basically all measuring the same thing. And again, are not very fine-grained. They're also not very fine-grained in terms of spatial locations. There are only a few stations around the world that measure these. The nearest to me in Virginia Beach is in Fredericksburg, Virginia. There's another one in Boulder, Colorado. But there are WSPR stations all over the place. And so you can maybe have a much finer spatial measurement as well as time measurement using WSPR. So how do I do it? Well, I'm a ham radio operator. My call sign is KN4NBI. And what I do is I send out a signal. This is all computer controlled, so I don't have to sit here and do it. But I send out a signal once every 10 minutes that's received all over the world. And everyone whose radio hears me, their radio automatically uploads a report to an internet site called WSPRnet. And then I can download and analyze the data for myself, or I can analyze the data for any other station who's part of the network. So if you look at the pictures there on the bottom, it's got me in Virginia Beach, KN4NBI. And in this particular analysis, all I looked at was how a fellow out in Oregon, KK6PR, was hearing my signal. And that's what's on the right. And what you can see there, that's basically an entire day. He couldn't hear me at all at night, but around 1700 Universal Time, there's a big peak. And another one around, I think it says 2300 Universal Time. So in other words, those two peaks are where he would have gotten the best reception of my signal. And then in the middle of the day, it's pretty iffy. And so this is the sort of plot that you could get, but you can get this with averages for 2 weeks. You can get it 10 minutes by 10 minutes, or you can get it every 2 minutes again if you need that kind of fine-grained detail. And you could then average, if I wanted to, say, all the stations in Oregon or all the stations on the West Coast. Or let's say I wanted to do an experiment with somebody who's sitting in a research station in Antarctica who wanted to do a psi experiment. I could look at the path to Antarctica and see what was happening in terms of radio reception in the geomagnetic field and compare that to what was going on with the psi experiment. So that's how I do WSPR. Now, here's what my WSPR station looks like. On the left is my commercial transceiver, which looks really fancy, but actually it's kind of a low-end one. You don't need a really fancy one. But you don't have to have a big one like that. On the right is actually a kit that I just finished building, and it's a little tiny one you can hold in your hand and you can take anywhere, hook it up to an antenna, and send a WSPR signal. So you don't need the big elaborate transceiver. And as I'll show you, in order to receive, you don't need a ham license at all. And to use the internet site, you don't even have to know anything about radio, as long as you have some idea of what you want to analyze. But this is what I'm using right now. And mine, in fact, is running right here on the laptop computer at the same time as I'm doing this PowerPoint. So that's what I'm using. And this is what happens when you then sign on to WSPRnet. And so I did this on February 22nd, a little earlier in the week, in the middle of the day for about an hour. And this is part of the download. And what it's showing is the time, what the frequency was, the signal to noise ratio, and a bunch of other data, and who was hearing me. So a station in Hawaii, AI6VN/KH6, heard me once. EA8BFK in the Canary Islands heard me a bunch of times. K4COD in Alabama heard me. K5XL in Texas heard me. And so this shows the signal strength, the distance, the azimuth. You can pull a lot of information out of this. And this is just a piece of, in that particular hour, there were 123 spots of my signal. And you may wonder, well, how do I know where these folks are? There's another website where you can look up any call sign in the world and find out where they are, and often they'll post information about what they're doing. So on my page on what's called QRZ.com, I mention how I do WSPR experiments on 20 meters. And some of these will show pictures of their big antenna farms or their very little antenna farms. My antenna is a wire over the garage, so it's not very elaborate because you don't really need an elaborate setup. But this is what you would get, and then you can process this in any statistics program. I just use Excel right now to process my data, but I may get more sophisticated later. And this is a map. I think I showed this. Well, I showed one map. This is a different map. This is a map of that same hour back on the 22nd, showing everybody that heard me. Again, it ranges from on the left there, a fellow in Hawaii, to on the right, there's one in Austria and one in the Canary Islands. And there is one down in Costa Rica. And then right in the middle, you don't see my call sign, but you see a call sign N4WQH. That's a fellow who's about 10 miles away. And he can hear me on what's called ground wave without it bouncing off the ionosphere, which is a really good control for just the general noise that's out there. And so theoretically, my signal should be absolutely steady at his station, but it's not. And so I can actually control for the noise level, and that can be helpful. And I think maybe the next slide shows that. So this is a typical map you can get. Again, you can set all kinds of different time periods, who you're listening to, who's listening to you, and any combination of that. So you could pick up just who happens to be there. But if you were doing a specific kind of anomalies experiment, you might arrange with someone, again, let's say I was studying psi, and there was an experiment here, and the receiver in a remote viewing experiment with someone in California, he might be in a park, a state park there near San Francisco, where KFS is, if you look over there on the left, and we'd have a radio link there and be measuring radio propagation at the same time as looking at remote viewing. Now, this is an example. This person happens to be a few miles away from me. So what I'm measuring here is not what's bouncing off the ionosphere in terms of my signal, but what it's actually measuring is the noise that's interfering with my signal at his station a few miles away over 24 hours. And I have an arrow there for sunrise and an arrow there for sunset. And so you can see that in the night, there isn't very much variability in my signal strength at his station. And in general, at night, the 20-meter band there's no ionospheric propagation at all, although that's not totally true. Whereas a little bit after sunrise, not only do you start picking up stations around the US, but also you start picking up ionospherically reflected noise from around the US. And so as the dots get wider in spacing, more variable, and get lower, what that's showing is my signal to noise ratio at his station is worse and much more variable. And that continues all day until a little bit after sunset, when it goes back to a quieter radio band and less variability. And so this is a control, so we could see how much of this is just due to noise and how much of it's due to different kinds of reflections from the ionosphere. So again, you can measure a lot of different things with WSPR, depending on what you're interested in doing. So you may be wondering, that's all very nice, you're a ham radio operator, you understand this, and you may be saying, I don't understand any of what this guy's talking about. So the question is, how can you do WSPR? Well, anyone can receive signals and upload reports. You need a receiver for it, but now they're making little receivers, which are basically, they look like a flash drive that you plug into your USB port, you hook an antenna to it, and your computer does all the work. And they're very cheap, so you don't need a big fancy receiver. But if you're somebody that doesn't even want to use a receiver, anyone without a receiver can just download reports from WSPRnet and analyze the data. And that's everybody, including all of you. You have to understand a little about what the data means. But for example, I just did this a couple days ago. I went and looked at KFS, which is a receive-only station in California in a very low noise area. It's in a state park in California. And you can see that he is picking up signals from Antarctica and from Australia. And in fact, his Antarctica signals are interesting because DP0GVN is a German research station on the ice in Antarctica, and DP0POL is a supply ship and research ship from Germany. And I tracked them by radio all the way from Germany, all the way down through the Atlantic Ocean until they dropped off their supplies there at DP0GVN. And since then, they've been kind of meandering around the Antarctic Ocean and South America. And so you can actually track this fellow on his ship. But again, if you wanted to have a well-controlled psi experiment looking at distance, maybe he'd have somebody there doing a little bit of remote viewing of penguins, and that you could then compare his success in remote viewing to geomagnetic conditions in the Antarctic. Now, getting a little bit off topic in the sense of not talking about how WSPR can be used, I just throw this in because it's something that sort of bugged me for a while, is one of the comments that skeptics often come up with about psi is that it's impossible because it defies the laws of physics and therefore it's not real. And so I wanted to refute the idea that psi couldn't be real because of the inverse square law, which if you remember your high school or college physics, the idea would be that because psi doesn't seem to depend on distance, it couldn't be real. The most recent people to talk about this in Skeptical Inquirer were Reber and Alcock. And the problem is that law only applies to forces and fields, like the force of gravity, which declines with the inverse square of the distance. But for communication, that's completely irrelevant. That signal-to-noise ratio is the only relevant parameter, not force or field strength. And a great example of that is what I'm demonstrating here with WSPR, that I have a 100 milliwatt signal, which is less than your home Wi-Fi, but it can be heard in Antarctica because WSPR can decode at minus 31 decibel signal-to-noise ratio. And so we have no idea how psi might work, but there's no reason to think that whatever mechanism it uses can't also pull signals out of incredibly high noise. And of course, we know that there is a lot of noise and it's very hard to get good results in psi experiments. Now, we still have a problem because in psi research, we don't have a way to quantitatively specify the signal level or the noise level, but it is clear that the inverse square law is just simply irrelevant. Again, that measures forces and fields. For communication, all that really counts is the signal-to-noise ratio if you've got any signal at all. And it can be an awfully tiny signal. Again, 100 milliwatts, that's your flashlight. That's your home Wi-Fi. Heard very nicely in Antarctica if you've got the right program. Again, just use an example in case that was a little bit unclear. One example is I listen to FM radio in my car, and I can hear equally good quality in the parking lot next to the transmitter at the local public radio station or 10 miles away at my home. And the quality only drops when the signal gets close to the noise level. And then again, using WSPR, my 0.1 watt signal, 100 milliwatts, like flashlight strength, is decoded equally well in Antarctica, Germany, and in Virginia, despite different numbers of bounces from the ionosphere. And the signal-to-noise ratio depends on geomagnetic factors. And again, that resembles psi results, where the quality of the results depends on the index of geomagnetic disturbance. So Persinger and Krippner looked at Krippner's old data on dream telepathy and found that basically the experiments only worked when the geomagnetic disturbance was very low. And there have been some other studies too, including some ones that suggest that things like poltergeist activity might actually increase when there are geomagnetic disturbances. And more work needs to be done, but it's clearly relevant. And WSPR may be a lot more sensitive than standard indices like the A and K and the AA index for measuring geomagnetic disturbances. These are the indices that have been used by parapsychologists and others. And an example I'll use from my own data is back in December, there was a geomagnetic storm predicted based on activity on the sun, and it ended up being a fizzle in that there was a very weakly elevated A index, but I was measuring propagation and found a huge effect. And so it shows that WSPR may be much more sensitive than some of these standard indices to what's going on as an adjunct to the things that other people are using to measure geomagnetic effects for their various anomaly studies. So I'll just show you an example here. I think I got a graph of it. So this is just my graph of my own data. And what you're seeing there on the x-axis is the date in December 2020. And then on the y-axis is in the blue is the number of spots of my signal. That is how many people uploaded a report of my signal to WSPRnet. And you can see that for several days prior to the geomagnetic storm, there's a certain level of people spotting my signal. It was predicted to arrive on December 9th. And if you look at the red line, which is the AP index, one of the geomagnetic indices, it shows nothing happened at all. But if you look at the people spotting my signal, it more than doubled within a couple of days and then dropped down to baseline levels. And so indeed there was an effect of this solar storm, but not one that was picked up by the standard geomagnetic indices. So again, this may be more sensitive, and it would seem in a lot of anomalies research we could certainly use some sensitive measures of things that are affecting our anomalies. Quickly mentioning here, because this comes up a lot in anomalies research, are something called Schumann resonances. And what Schumann resonances are is lightning creates radio waves that reverberate between the Earth and the ionosphere around the Earth. And so they go all the way around the Earth. And the first resonant frequency is about 7.8 hertz, which is near the alpha brainwave frequency. And so there have been some studies suggesting that the Schumann resonances, which again are affected by geomagnetic effects, just like everything else with radio waves, that these could be affecting our brain waves, our health, our heart rate, and a lot of other things. And so that's what those are. So just give you a couple of other applications possible for WSPR and then open it up to questions. One, again, is the fine resolution measure of ionospheric variables related to global coherence. There's a group called the HeartMath Institute, and they have presented at SSE meetings. I believe York Dobbins was co-author on one of their papers, and they've looked at the traditional ionospheric geomagnetic measures, and down on the right-hand side is just an example of all the ones they used, and found some rather strong relationships with human physiology. And so WSPR might offer an additional measure with finer temporal and spatial resolution that could be added to what they've done in the past and measure these effects on human physiology. And another one, again, is fine resolution measurements of geomagnetic disturbance related to psi experiments and experiences. So a lot of this work had been done by Michael Persinger, and then Krippner and Persinger found evidence for enhanced congruence between dreams and distant target material during periods of decreased geomagnetic activity. In other words, when the geomagnetic field is quiet, not only is that generally good for radio propagation, but it seems good for psi propagation too, whatever that might be. So again, here we have a measure with finer temporal and spatial resolution. So none of this has been applied yet, but the opportunity is there. And I think that's the last one. Oh, not quite, though. This is the last one. This might also be useful for other anomalies. For example, in astrology, astrology is all about subtle solar and lunar and planetary effects on biological systems. And WSPR might be helpful in measuring some of those because, again, it's very sensitive to disturbances due to solar radiation. couldn't hurt looking at it for other kinds of effects on biological systems. Another one I find quite interesting is UFO experiences. It might be helpful in measuring local geomagnetic disturbances in UFO cases. I was reading a book by John Keel about some UFO cases in West Virginia, and was just curious. So I looked up in the database, and there were some huge geomagnetic storms right around the time that everyone was reporting these UFO experiences in West Virginia. So again, potentially helpful in measuring some things that might help explain some of these kinds of anomalies. And there is my list of references. I'll leave it up for a little bit here, so I know that this is being recorded, so if anybody wants to look at any of the references, there are many, many references on studies that have been done using these variables, and the WSPR pages have references to how WSPRnet works.
Great. Well, thank you so much. That was very interesting talk and thought-provoking. And it's now time for some Q&A. And so I see we already have one question in the chat window, which I will relay to you, unless you can, in the questions window. Can you see that, Doug? If not, I will relay that to you.
Questions. Yes, I've got the questions open. I see 2 questions.
There you go. So if you want to address those rather than having me read them to you, and then anyone else who wishes to either chat or in the questions, not the chat box, in the questions box to write your question, or you can raise your hand and then we will call on you and turn on your camera and microphone and you can talk directly with Doug if your question requires a little more than just a sentence. All right.
Okay, so I can see the first question here, and the other one says I have the same question. So the question was, does the WSPR algorithm require a continuously repeating signal to analyze? And the answer is no. Actually, you can set it up to do it lots of different ways. Some people want to test their antenna and simply broadcast one WSPR signal. That's it. And then they look and see who all around the world has spotted that one transmission. On the other hand, I've been doing it every 10 minutes for the past a little over a year, night and day, except for things like thunderstorms when I have to turn off my equipment. And the reason for that is because there are a lot of people who then can listen to me and know they've got a reliable signal. So if they're testing their antennas, they know that I'm there and have got a continuous signal. And there are a number of people who are always on, and then some who are just on for a very small amount of time. Because of the noise, there are issues of you may want to do some averaging in order to come up with good measurements. And so just a single transmission isn't the greatest idea in the world. Again, mine is every 10 minutes, which is kind of the default standard for WSPR. I did a little bit of stuff with it every 2 minutes. And the only trouble with that is it generates a huge amount of data. And then also not as many people can use the channel at the same time. So not very many people do it every 2 minutes. So I did it for a couple of hours here and there to do some experiments, but decided to, it would just annoy people if I did that too much. But there's actually a WSPR station over in Norfolk, near where I am, on the battleship Wisconsin. It's a ship museum, and they have an antique radio club there, and they put in a WSPR transmitter as well as their World War II type transmitters. And for a while, we're running that one 24 hours a day. But I think with COVID, they weren't able to get there to maintain the thing because it's a museum that was closed. But at any rate, you can be very flexible.
I see that we have several more questions in the questions box. We also have York Dobbins, who has raised his hand and would like to have the microphone. If you are okay, I will give the microphone to York. We always like to.
I know that York is co-author on one of the papers I cited, so you can see what he has to say.
All right, let's just see if this works here. Providing mic to York Dobbins, we'll see.
The WSPR system obviously involves some form of fairly high-end data processing to extract these very weak signals from a strong noise background. Have you considered applying the WSPR algorithm or algorithms directly to anomalies data? This would, of course, have to be high-volume anomalies data, such as the GCP or some of the stuff people have done with very high speed REG devices. But had you thought of looking at high volume anomalies data to see if you can find patterns in what mostly looks like random noise to see if there actually are structured signals buried in there.
Well, that gets way beyond my expertise because I just use it, but have no idea how it was actually programmed. The guy that actually did it is at Princeton, near your old stomping grounds. Joe Taylor in the physics department there is the one who developed the WSPR algorithm with a number of his colleagues. And I don't know if any of them might have an interest in applying things. One of the problems with applying WSPR to some anomalies is it requires very careful time synchronization, although they're developing ones that don't require time synchronization, because it's hard to get time synchronization with a lot of anomalous data. But it's a group based at Princeton, but they're all over the country. One of them is out in, I think, University of Illinois and various other places in the country that work as a team. And if you go to the WSPRnet site, it's got links to their pages. I think it's a physics page at Princeton is where Joe Taylor's site is, but they've got links to all the people doing the WSPR development. How it all works is a little bit beyond me. Basically, they use a lot of signal processing, but it's not so complex that you can't do it on a laptop. And their software is all free. If you just download it and start it up.
All right. Thank you, York. So the software itself, the actual algorithms that do the analyses are running on your local machine. This has not been analyzed on a central server and put up already processed? Well,
both. And so what happens is I sit here with this screen right now. I've minimized my screen I won't show it to everybody, but essentially while I'm running this on the receiving side, when I'm not transmitting, it's constantly displaying everything I'm receiving and decoding. Then every 2 minutes, it uploads it to the WSPRnet site on the internet. So that if I want to look it on the internet, I can just log on to WSPRnet and see who's received me and who I've received. But I'm seeing everybody that I've received and decoded their signals in real time, just sitting here on my screen. So they've got processing within your own computer, but then processing at WSPRnet site. And then several people have got their own sites where they've written algorithms to do other things. So a fellow in Australia wrote the program that does some of the graphs and maps I was showing. He takes all the data and puts it into graphs and maps. And so you can download all of his graphs and maps. So it's a big open source project with people all over the world coming up with clever things to do with it.
Terrific. Can you see the questions in the questions box still? We have several.
Again, they sort of scroll down. So let me scroll back up again.
Yeah.
Okay. The first one I see here was, do I see psi as potentially analogous to WSPR and separate from EM signals? I have no idea. I don't think anybody knows what psi is, although you'll certainly see a few people playing with physics to try to figure it out. Who knows? The interesting thing to me is that whether it's electromagnetic or not, and I would say probably not, whatever is going on seems to be affected by electromagnetic phenomena. Now, that may just be because they affect humans, not necessarily psi. And so it looks like the same kind of phenomena that affect psi may be affecting heart rate variability and other physiological variables, but there's certainly a parallel there. But what's actually going on physically, I haven't the slightest idea. I do know there are some physicists who've been trying to figure it out. I'm not sure that they know what's going on either. Very hard to do. Okay, the next one, for psi experiments, what frequency range do you look at and what kind of signal? Well, again, for what I'm doing, it's not psi experiments. For any kind of experiment, there is an enormous range of frequencies. WSPR is now being used in the ham radio bands. Those range from 135 kilohertz, which is just a little bit above audio that you could hear, very, very low frequency radio band, all the way up to about 1.2 gigahertz, which is kind of up around where your cell phone works. And there are about 10 bands in there. I'm using one just about in the middle called the 20 meter band. The main reason being I have an antenna for it over my garage. Also, it happens to be a very good long distance band, and that's what I was interested in. But there are a wide variety of bands that people are using, and it all depends on what your particular application is. And it doesn't require you even to use ham radio bands. If you're going to use radio, you need to use ham radio bands. But York was talking about using it in some other thing directly on anomalies, and some people have done things like modulated light waves and received them across the street and seeing how well it works. And so anything that you can put a signal on, potentially you can use WSPR to decode the signal in very high noise environments. So, lots of possibilities. Okay. Next one was, if the signal is not repeating, that would require the noise figures to be extremely consistent to make any deviation from the noise figure to be identified. The way it works is that each block is 2 minutes long, and it has a huge amount of redundancy in that 2 minutes, and that's how they extract the signal. If that isn't good enough, again, you can do multiple whisper transmissions. And so a lot depends on how much noise you've got and how precise you want your answer. But the actual blocks that are used in the whisper signal are 2 minutes full of very, very redundant forward error correction. Okay, and then next one was, does this process apply only to electromagnetic signals or magnetic and or electric? Any kind of signal at all, including light, including sound. Again, it was intended for use with ham radio bands, but people have tried all sorts of other applications. You could even use it, say, at a rock concert, slip a whisper signal in and detect it, 6 blocks away in somebody's house with a microphone if you wanted to. It should work. And actually, it was originally, the original thing that Joe Taylor designed was for moon bounce, which is incredibly noisy, low signal. Send a radio signal up to the moon and bounce it off. And everybody started using it for regular ham radio. And so he and some other people rewrote the algorithm to make it more useful for ham radio. They still have one for moon bounce. So they keep playing with different kinds of systems. Next one was, so there's no sync signal, only time dependent. It's time dependent, and the way whisper runs, it has to be synchronized to universal time, and typically you use the NIST computer server. Once you've got it synchronized, if you've got a good enough clock, you can just keep it synchronized for a long time. Some people use GPS to synchronize the time, but it does have to be time synchronized. However, they're working on algorithms, and they already may have one for some of this digital stuff without any time synchronization, but that's not the way whisper works right at this point. Then question, where can I download your citations? They were on that last slide, and I think, Mark, this whole thing will be posted somewhere?
My understanding, yes. I'm not sure about the Q&A, but
the slide will be on the recording.
Right, the slide will be on the recording, so you can just watch the end of the recording.
Somewhere on the SSE side, I guess, Annalisa knows
right.
where.
And would you be receptive to people emailing you and requesting that?
Sure, I'd be happy to send it to anybody who wants it. My email is doug.richards@cox.net.
Terrific. I see some more questions.
Okay, somebody did a screenshot of the citations. That works, yep. Okay, next one was, are you analyzing a CW signal or some kind of modulated RF? That's for people who understand what this is all about. And the answer is, the way it works is that it is a set of, I believe, 4 tones that are amplitude modulated and have a very, very narrow bandwidth. And so the bandwidth is on the order of just a few hertz, and it's just a set of 4 tones. So it's basically a frequency shift keying modulation with 4 tones. And the Whisper website has all the technical data on how the algorithm actually works. But I think that's what it is. They have a number of different kinds of encoding for a number of different kinds of digital ways of talking. So, for example, FT8 uses 8 tones. JT65 uses 65 tones. I think Whisper uses 4, but they're just audio modulated tones. And the reason for that is that you can use the sound card in your computer to decode all this stuff. You simply use the sound card plugged into your receiver. And some people who don't have very fancy equipment actually hold the microphone for their transmitter up to the speaker in their computer in order for it to work. Your baby crying and your cat meowing will interfere with that, but I have seen people doing that on YouTube, and it works. It's just kind of a pain. Mine plugs into the computer, but that's why all these things are audio tone modulation. And what were the audio signals you heard from Mars a few days ago? Haven't a clue.
I believe they were actually believed to be Martian wind over the microphone.
Ah, okay. Now, interesting thing, you may wonder, how do signals get from Mars to here? And the answer is, for their video and audio, they're using very similar kinds of algorithms in order to take extremely weak signals and pick them up and turn them into nice pictures and sound down here. So there's a lot of people are doing this kind of signal processing for all sorts of things. And this just happened to apply to something that anybody can do with their laptop computer.
All right, let's see. I'm looking. I don't see any more questions or raised hands.
One just popped up.
Oh, there you go.
Okay, so does it have a limit on how low the signal is with respect to the noise? Yes. For whisper, it's negative 31 dB related to the noise in a band around the signal. And for more specifics, you'd have to go to the whisper site and see exactly how the algorithm works. But they've got several different kinds of signal processing with different noise thresholds, but it's negative 31 dB. As far as the psi signal, no one even knows if psi is a signal. That's one of the problems. We really don't know what's going on with psi and how we'd apply the algorithm to it. So again, York had an interesting question that I have no good answer to. It's something that no one really knows, but certainly trying some of these signal processing things with these sorts of weak signals, that or Roger Nelson's random number generators, is certainly worth a shot and see what comes up. There might be a way to do that.
Terrific. Let's see if we have any more questions. All right. So thank you very much. Everyone, give you a virtual round of applause here. Thank you very much. Very interesting talk.